Hello friends, welcome to my channel. This is Thermodynamics and Power Plant Isro question paper part 7. Question is a sample of gas gamma equal to 1.5 is taken through an adiabatic process in which the volume is compressed from 1600 centimeter cube to 400 centimeter cube. If initial pressure is 150 kilopascal, then how much will be the final pressure in the process? Data given are gamma equal to 1.5, V1 is 1600 centimeter cube, V2 equal to 400 centimeter cube, initial pressure P1 is equal to 150 kPa kilopascal, process is adiabatic, PV to the power gamma equal to constant, final pressure in kPa, P2 we have to calculate, so we will use this one, P1 V1 to the power gamma, P2 V to the power gamma. So we have to calculate P2 equal to P1 into V1 by V2 whole to the power gamma. So P1 is 150 into 1600 by 400 whole to the power 1.5. Here I will tell you how we will solve this one. By 400 whole to the power 1.5. It's 4 to the power 1.5. We can write it as 2 minus 0.5 or half. It's 4 square by 4 root over. It's 16 by 2. It's 8. So it's 150 into 8. Then 1200 kilopascal or kilonewton per meter square. From option it's A. A is our answer. 1 mole of a monoatomic gas is taken through a cycle ABCDA as shown in PV diagram column 2. Give the characteristics involved in the cycle. Match the process A to B with the processes given in column 2. Process A, B only we have to calculate. So here we will take A as 1 and B as 2. And at B the volume is 3V. At A volume is 3V and B it's 1V. So it's compression process, constant pressure is 3P. So we have to calculate process AB. Here it's 1V, 3V and 9V. 1V, 3V, 9V. Pressure 1P, 3P. So this is 1. Here it's 2. At B it's 2. During process AB, P1 equal to P2. P1 is pressure at A and P2 is pressure at B. So volume V1 equal to 3V and V2 volume at B is V. Then P1 V1 by T1 equal to P2 V2 by T2. From here P1 same, both are 3p cancelled. Then V1 is 3V by V2 is single V, T1 by T2. So V1 cancel, T1 by T2 equal to 3. It's positive. And T1 equal to 3 T2. So T1 is greater than T2, or TA is greater than TB. Then we will go for internal energy change, mCv dt. For unit mass, m is 1, or mCv dt is T2 minus T1, or temperature at B minus temperature at A. This one we already know. T2 is less than T1, so this term is negative. So del U, or change in internal energy, is negative, or internal energy is decreasing. Then for work done it's P into P dV is V2 minus V1. It's decreasing. V2 is less than V1, so this term also negative. Then heat transfer, it's del U plus del W. Del U also negative, del W also negative work done, so heat transfer will be negative. So process AB, del W is negative, or work done on the gas. Then change in internal energy, this is also negative, or internal energy is decreasing. Del Q also negative, or heat loss. So from option we have to check. Process AB signifies work is done on gas T, then internal energy decreases, then heat lost. So PRT from option C is our answer. A steam engine intakes 100 gram of steam at 100 degrees Celsius per minute and cools it down to 20 degrees Celsius. Calculate the heat rejected by the steam engine per minute. Consider latent heat of evaporation of steam is 540 calorie per gram, and Cp is equal to 1 calorie per gram degree Celsius. It's a steam engine. Mass given 100 gram. First temperature is 100 degrees Celsius and cools down to, so T2 is 20 degrees Celsius. And latent heat of evaporation, it's 540 calorie per gram. Then Cp 1 calorie per gram degree centigrade. So we have to calculate the heat rejected by steam engine. Q total here, or heat rejected total, is in terms of at 100 degrees Celsius it's latent heat, then Q mCp dt. So mass into first q1 plus q2. q1 is mass into latent heat plus mcp dt. dt is 100 degree Celsius to 20 degree Celsius. Here mass is 100 gram, 100 into 1, latent heat is 100 into latent heat is 540 plus mass is 100, Cp is 1, then dt 100 minus 20. 100 take common, 540 plus 80. So 100 into 620. It will come 62 into 10 to the power 3 calorie. So from option all are in 10 to the power 4 term. Then 6.2 into 10 to the power 4 calorie. From option C is our answer. A heat engine operates between a cold reservoir at temperature T to 300 Kelvin and hot reservoir at temperature T1. It takes 200 joule of heat from the hot reservoir and delivers 120 joule of heat to the cold reservoir in a cycle. What will be the efficiency of the engine? Only efficiency. So actual efficiency we have to calculate. It's a heat engine. Hot reservoir and cold reservoir. This is hot reservoir. Then it's cold reservoir. Here temperature is T1. Temperature T2 given. T2 is 300 Kelvin. T1 not given. It takes 200 joule of heat from hot reservoir. So it's Q1 and Q2 deliver 120 joule of heat to the cold reservoir. This is work done. Heat engine. We have to calculate the efficiency of the engine. Efficiency is actual efficiency we have to calculate. Work done by heat supplied. So work done is Q1 minus Q2 by heat supplied is Q1. 200 minus 120 by 200. It's 80 by 200. It's in percentage terms. So multiply 100 to it's 40% actual efficiency. From option B is our answer. The difference between two specific heats Cp minus Cv equal to R by J. This relation is valid for perfect cases. J is joules equivalent. Cp, Cv are all terms already discussed. A process in which no heat is supplied or rejected from the system and entropy is not constant is known as no heat is supplied or rejected. So del Q equal to 0 and del S is not equal to 0. Isothermal process not possible. Isentropic process is del S is constant, del S is 0, entropy is constant, so B also not possible. In hyperbolic process, gas is heated in such a way that product of pressure and volume remains constant. P into V is constant in case of hyperbolic process, so it's also not possible. In polytropic process, del S is not equal to 0 and del Q equal to 0. C is our answer. Thank you friends. Thank you for my watching. If you like my video, then subscribe it.